In this video, I want to take you through a key step in the derivation of the eigenstates and the eigenenergies for the quantum simple harmonic oscillators. Now we should say eigenstates and eigenenergies of what? Of the time-independent Schrodinger equation. So this is an eigenvalue equation. We have the Hamiltonian operator operating on psi, gives us some value, some eigenenergy E times psi. We're looking for solutions to that. In doing this, I'm following second edition of Griffith's quantum mechanics text, page 44. All right, we need to use some previous results. Previously, on previous pages of Griffiths wrote the Hamiltonian in terms of these A plus and A minus operators like this. And this actually contains two equations. So we can either take the top signs, the plus here, the minus there, and the plus there, or we could take the bottom signs, the minus here, the plus there, and the minus there. So this contains two equations. We also need to utilize this result for the commutator of the A minus and A plus operators. That commutator turns out to be 1, which if we want to unpack with the definition of the commutator, we can rewrite like this. All right, so going with all that, I'm going to follow Griffiths here. He says, now, here comes the crucial step, and this is indeed crucial. I claim that if little psi satisfies the time-independent Schrodinger equation with energy E, that is, if we have this, if little psi is indeed a solution to this equation with corresponding eigenenergy E, then the state constructed by operating on little psi with A plus, which I'm just going to call A plus psi, then A plus psi satisfies the time-independent Schrodinger equation with energy E, this E that we had corresponding to this original psi, plus h bar omega. And written out in symbols, Hamiltonian operating on A plus psi will give us some value E plus h bar omega multiplied by that function A plus psi. So if you look at this, this is an eigenvalue equation. This and this are the same function. So A plus psi, if this were the case, would be an eigenfunction of the Hamiltonian, and the corresponding eigenvalue would be E plus h bar omega. All right, so here's the proof. To prove this, Griffiths just constructs this. He just operates on this proposed eigenstate A plus psi with the Hamiltonian and tries to see what comes out. So here we go. Let's operate on this state with the Hamiltonian. So we're going to swap the Hamiltonian out for one of the forms of this. We're going to choose, for reasons that become apparent, the top signs. So the plus here, the minus there, and the plus there. So we put that in right here. So here's the Hamiltonian operating on this state. Great. We're going to just distribute this onto that, and we get this result. We can take this 1/2, since it's a constant, we could put it there or there, doesn't matter. Let's imagine putting this 1/2 back over here, and then we can peel off an A plus. There's an A plus right there, there's an A plus operator right there. We can imagine factoring that back out of this, and we'll get this expression. And if what I just said bothers you, take this, redistribute all this through onto this, and we can get that. All right, now we can change the order of the h bar omega and the A plus, right? H bar omega is a constant, so it can pass through the operator without any problem. So in this next step, all that's happening is we're just going to pull the h bar omega through to there. And so we've got A plus that's still factored out of everything. We've got our h bar omega, but now we're going to fiddle around with this stuff in here. So notice here I have an A minus A plus. Here I've got an A plus and an A minus plus 1. The 1/2 is the same, the 1/2 is the same. Well, there's nothing magical that's happened there. We've just used this commutator relationship to substitute A minus A plus with A plus A minus plus 1. So if you solved this equation for A minus A plus, you'd get 1 plus A minus. That's just that right here. Great. So this is the same as that. So it's just a slick substitution. Now the next step, Griffiths probably should have shown one more step in here to go from this to this. So I'm going to take you through this. It's kind of cool. Now, look here. I've got an h bar omega, an a plus, a minus, and a 1/2. And I've also got this 1. Let's ignore the 1 for a bit. If we didn't have the 1 here, I'd have h bar omega, and then these parentheses, a plus, a minus, and a 1/2. Well, that's the same thing right here. I've got h bar omega, a plus, a minus, and plus 1/2. So, except for this 1, I've got the Hamiltonian operator. Now, what I actually have is h bar omega distributed onto that, which is the Hamiltonian, plus h bar omega distributed onto the 1. So what I have then, the h bar omega distributed onto the 1, that becomes this h bar omega here. The h bar omega distributed onto this and this, well, that's just the Hamiltonian. And the a plus operator is still just hanging along outside, sitting out here. So all we've done is factor the h bar, or distribute the h bar omega through onto here, replace the appropriate parts with the Hamiltonian operator, and rewrite it this way. Okay, so now what we can do, we're still going to leave this out here. What we're going to do is we're going to operate on little psi with this. Distributing this onto this, well, we'll have, for the first part, h bar operating on psi. That'll give us e times psi. And this part, operating on h bar omega by multiplying by h bar omega, is just multiplying by h bar omega. So we'd have e psi plus h bar omega psi, and we'll just factor the psi back out. Now, so going from here to here is just a straightforward operation. Now we're almost done. E plus h bar omega, that's just a value. That's a number. That can pass through the a plus operator, or to put it another way, I can pull the a plus operator through here, leaving us with this. And now we're done. So let's look at what we've got. We've got the Hamiltonian operator operating on this state, a plus psi, equals some value, e plus h bar omega, multiplied by that state, a plus psi. So this equation has this form. That is, I've got the same function here and here. I've got the Hamiltonian operator, and I've got a value. So this function, constructed by operating on the original function with the a plus operator, is in fact an eigenfunction of the Hamiltonian operator, and it has this corresponding eigenvalue. All right, so let's sit back and take stock of what's happened here. What we've shown, in essence, is if we could just solve this equation and find one eigenstate of the Hamiltonian and one corresponding eigenenergy, then we can construct another state with h bar omega more energy than the first one by taking the original state and operating on it with the a plus operator. But once we got that, we could do it again, because this is an eigenstate of the Hamiltonian with this energy. We could operate on that state with a plus and get another state with h bar omega more energy, and so on and so on. So if we could just get one solution to this equation, one eigenstate and one corresponding eigenenergy, then we have here a machine to construct solutions with ever higher energy, with increments of energy h bar omega each time higher than the previous one. In the next paragraph on page 44, Griffith sets out to show that if little psi is an eigenstate of the Hamiltonian with energy eigenvalue E, then the state constructed by operating on little psi with the a minus operator is also an eigenstate of the Hamiltonian, but with energy eigenvalue E minus h bar omega. So basically we're trying to show that if this is true, then this is true. So here we go. We start by just constructing this and seeing what emerges. So that's what we have right here. Then we can swap out the Hamiltonian operator using this. However, in this case, we're going to use the bottom signs, the minus here, the plus there, and the minus there, and that's what we have here. We can then distribute this onto this, getting this, so the proof is proceeding pretty much as the previous case that we had for the A plus psi. Now we need to swap this out. We're going to swap this out for this, but we can't just swap it directly. We've got this relationship here, so we've got to use the commutation relationship to put this in terms of that. We then do some regrouping. We can note that h bar omega a minus a plus and h bar omega minus 1/2. That can be written in terms of the Hamiltonian. So this becomes the Hamiltonian operator, and the 1 and h bar becomes that h bar right there. So that proceeds very much as in the previous paragraph. We can then we can take the Hamiltonian operator, operate on the little psi. We get this e here, minus h bar operator operating on psi. That's just a multiplication, so we get that there. We can then bring this through the a minus operator, and we can regroup the a minus operator operating on the little psi. We get this. So I've gone through it much faster than in the previous case, but in the end what we have is the Hamiltonian operator operating on a minus little psi gives us this energy, E, the original energy, minus h bar omega times a minus psi. So a minus psi is an eigenstate of the Hamiltonian with this energy eigenvalue. And so we've proved the proposition. And so I just bring you here then to Griffith's conclusion. I'm just going to read it straight because it's beautiful. Here then is a wonderful machine for generating new solutions with higher and lower energies. If we could just find one solution to get started. We call a plus and minus respectively the ladder operators because they allow us to climb up and down in energy. A plus is known as the raising operator and a minus is known as the lowering operator.